Supercon in 2021 that was also about creative circuit board assemblies. And I will cover some of the projects from the Remoticon talk here today, along with some newer creations. So a brief backstory of how I came to even start making printed circuit boards. I worked as a software engineer in the 90s and had almost no experience with hardware at that time. I retired in 2000 to raise 3 boys and was a stay-at-home parent when I encountered programmable electronics for the first time in 2012 while coaching my son's Lego robotics team. They were named the Fire-Breathing Chickens. I had just been introduced to Arduino and decided to enhance the robotics team sweatshirt with sewable LEDs and Arduino LilyPad. And it was the best sweatshirt at the competition, and I was hooked on wearables. And it was wearables that motivated me to learn circuit board design. After my son outgrew his desire to have me coach his team, I was volunteering teaching elementary school students to learn to code using the Microbit microcontroller, which is my personal favorite physical computing educational platform. But I wanted to reach kids who might not be interested in robotics or electronics, so I decided to create a wearable educational coding platform. And that became a system of illuminated bags that housed an LED microbit expansion board. The board sits inside the bag's front pockets with LEDs that shine through small perforations in the pocket. I learned enough EagleCAD to design the bright board, as I called it. One significant design challenge was how to consistently align the LEDs on the circuit board with the hole pattern in the front of the bag. And the solution I came up with was sewing snap connector halves into the bag pockets and installing the matching halves inside the circuit boards themselves. And these were garment snaps, not PCB components. I installed all the snaps myself with a snap setter because I had no idea how to request that from the PCB assembly process. But I have been using unconventional components in my circuit boards for quite some time now. And the builds in this talk have a number of common elements. Besides just looking awesome, addressable LEDs allow circuit boards with very, very simple circuits to form really interesting looking assemblies. You only need to transmit power and signal between adjacent boards to make a functional full assembly. I also really like the challenge of making modular builds that can be reconfigured and scaled easily. And because modular builds incorporate a lot of PCBs sometimes, I try to keep components cheap. And one recurring challenge that will appear in this talk is deciding when to use electrical components for mechanical purposes. A lot of circuit board components really look like they should provide good support or mechanical function, and it's always tempting to use them that way, and it doesn't always pan out. So the first PCB assemblies I'll show are static structures. In 2020, I created my first modular circuit board system. I wanted light tiles like the commercial Nanoleaf wall panels, but I wanted them to be freestanding and reconfigurable sculptures. So the base elements of these light tiles are just regular triangle and hexagon shaped PCBs with side emitting LEDs at each corner that face inwards. And a translucent white acrylic layer sits over the surface of each tile to diffuse light over the entire front of it. And each tile's layers are held together by nylon screws. But for the build to be reconfigurable and freestanding, the tile connectors needed to be both detachable and sturdy. I designed a second smaller set of printed circuit boards to work as board-to-board connectors, which screwed to the backside of adjacent tiles. The connectors had spring contacts to transmit signal and voltage to solder pads on the back of each tile. And a thin acrylic buffer layer sits between the connector and the tile that keeps the contacts from getting crushed. And I became really fond at this project really started my interest in spring contact connectors. They're easily detachable, generally inexpensive, and the mating connector is a solder pad, which is free, essentially. And another thing I learned from this build is that for spring contacts to work well, their mechanical configuration should be stable, so redundant contacts can be a good idea. And these 2 light tile sculptures are still displayed in my office, and ironically, despite my objective of making them rearrangeable, they're still in their original configuration. So I still did want to create light tiles that could be rearranged as easily as building blocks. So the follow-up light tile project actually has 2 levels of modularity. I designed a single set of LED PCBs to form the sides of the tile. Each PCB had 2 addressable LEDs, and they can be assembled in different quantities to make any geometric shape with congruent sides. The tile's top and bottom faces are made from translucent acrylic or 3D printed filament, and the faces have slots to hold the tabs on the PCB's top and bottom edges. The PCB sides have castellated side edges that allow the PCBs to be soldered together directly at any angle, and these castellated edge connectors transmit power as well as input and output signal from the LEDs on each PCB side, and also they take LED output signal from all the LEDs on the entire tile, so any side of a tile can be designated as an input or output side. The input-output function is selected with a slide switch, which, as it turns out, was kind of overkill because if you're rearranging an assembly, you can just rotate a symmetric tile to put it in place, and if I made them again, I'd use solder jumpers. But the adjacent tiles do connect detachably, nicely, with header pins, and this project met my goal of being easy to rearrange with the trade-off that the final assembled shape is only stable if it's on a horizontal surface. And after 2D light tiles, things moved into 3 dimensions. I pondered the idea of a light-up polyhedron and came up with the concept of an illuminated orb that I brought to Supercon in 2022. While it doesn't use custom printed circuit boards, this design motivated later builds that did. The basis for the orbs are LED cubes constructed from standard off-the-shelf square matrices. Different size matrices yield a range of different orb sizes, and special 3D printed covers extend the light from each matrix to the surface of a sphere. Because all parts are store-bought or 3D printed, it's a manageable and accessible build that I wrote up for volume 84 of Make Magazine. And the illuminated animations on the largest orb surface there are controlled by Ben Henke's awesome Pixel Blaze LED controller, which I love. Yes, massive shout out to Ben, who couldn't make it this year. But it really bugged me that these patterns are so gorgeous and I could only see half the pattern at a time. The far half of the sphere is invisible. I really wanted to see, all the LEDs at once. So that inspired the next build, which did use custom printed circuit boards. I decided to make polyhedral shapes from polygon PCB sides with cutout centers to make the structure see-through. For a chain of addressable LEDs to form an unbroken signal path along all the PCB sides without using additional circuitry, you need to make sure you have a plan to avoid the signal hitting a dead end as you navigate all the faces of the polyhedron. And I ended up building a 20-sided icosahedron. Oh, whoops. So just to make sure that the signal path worked, before I designed the tiles, I folded the polygons out of paper and traced the path with a pen to make sure it worked. And I ended up building a 20-sided icosahedron, 32-sided truncated icosahedron or soccer ball, and 60-sided deltoidal hexacontrahedron. The shapes with the, yeah, it's a lot. The shapes with regular polygon faces used circuit boards with one side as signal input and the rest as output. And to make the actual signal path work, the kite-shaped tiles required 2 input sides on one short and one long edge, and the opposite sides being output signal edges. And version 1.0 of these polyhedral builds had some issues. And I initially tried to combine electrical and mechanical function with custom small PCB connectors that use 2x2 right-angle header pins to connect adjacent circuit board faces. The angle of the header pins matches the angle of adjacent polygon faces. And these custom connectors looked super substantial and sturdy on the screen, but were tiny and wobbly in real life. And objects in CAD are always smaller than they appear. Fortunately, I prepared to fail by leaving holes in each PCB corner and shored up the structures with 3D printed corner supports that attached with small screws and nuts. And after losing dozens of M1.6 nuts during the assembly, I decided all future 3D printed connectors would use heat set inserts. So another problem with Polyhedra version 1.0 is that my inspiration was the light tiles, so I put LEDs at the corners facing inward to provide edgelit illumination to transparent acrylic that I inserted in the cutout. And the intent was to have light in the middle of each tile visible from both sides, but what ended up happening is it obscured the view through the polyhedron and made it impossible to physically access the interior to fix any problems once it was assembled. Version 2.0 fixed these problems. It had mechanical support from 3D printed corner connectors and wires soldered between adjacent PCB faces for electrical connection. And I made several changes to make it easier to see the light all the way across the entire structure. The PCB cutouts were enlarged, and side-emitting LEDs line the entire perimeter of each face in this build. Translucent 3D printed covers diffuse the light, and because they extend slightly into the center cutout, the LED patterns are visible from both sides of each PCB. And to keep LED spacing uniform on the kite-shaped circuit boards, since the short to long edge ratio was about 2 to 3, I put 4 LEDs on the short edge and 6 on the long edge, and this ended up totaling 1,200 LEDs in the deltoidal hexacontrahedron. I'm getting used to saying that. And so it turns out if you have that many addressable NeoPixel or WS2812 LEDs in a single series, it takes long enough to transmit data down the chain that you can slow like really complicated animations. So when it came time to illuminate the structure to keep frame rate high, I used 2 separate Pixel Blaze controllers, you see right there. Their patterns synchronized over Wi-Fi, and each Pixel Blaze is responsible for computing animations for half the pixel map. And in order to find the LED positions for the pixel map, I used p5.js, which is a JavaScript library for graphics and data visualization. I wrote a program that took LED positions on a single PCB and then used built-in p5.js functions to rotate and translate the faces and compute the rest of the LED positions. I love the way these turned out. The truncated icosahedron and deltoidal hexacontrahedron builds are on display in my house, and I would really love to try making more different shape polyhedra if time and tariffs allow. So now we're going to pivot to discussing rotating PCB assemblies. This build that I called Bendy boards was in my Remoticon talk. It's a modular, flexible series of connected links that function as slip rings made from 2 PCB layers with an acrylic thin buffer layer in between. One side of each link has concentric circular solder pads, and the mating side has spring contacts, 2 per ring that are aligned tangentially to the circular solder pads to minimize rotational torque on the spring contacts. The rotation axis is a nylon push rivet, and this build could be more compact if the center pivot were conductive, but push rivets are super cheap, strong, and flexible, and I haven't yet found a good electronic substitute. And this design emphasizes expandable modularity, so pivoting links transmit power and signal via detachable mezzanine connectors with 2 small screws for mechanical reinforcement, but you can make it as long as you'd like. This build required a lot of iterations, mostly focused on getting the dimensions and tolerances right. And the limiting factor for the length of an assembly is just making sure the voltage doesn't drop too low to light up the LEDs. So I also made a smaller proof of concept project using the same slip ring design. In this build, the concentric solder pads are arcs rather than full circles. And so this PCB fidget spinner contains 3 standard RGB LEDs, which just change color based on rotation angle, no IC required. And last year's Super Contest, let me revisit Bendy boards, and that's how Bendy SAO was born. The pivoting circuit board idea worked great to make a wacky, waving, inflatable, arm-flailing tube man. And for aesthetics, I streamlined the pivot joints, which reduced the maximum possible angle of rotation in each link, but it still moved pretty well. And as a terrific bonus, it turns out that green printed circuit boards work both aesthetically and speed up design iteration. Illumination comes from LEDs on the underside of the 4 top layer circuit boards with light diffusing through clear FR4 in the portions of the board where copper and solder mask are blocked. And having surface mount components sitting between the PCB layers required extra cutouts in the 1.6 millimeter acrylic buffer layers. It was a bit of a challenge to make sure they retained their structural integrity as buffers in the final build. Bendy's 4 pivoting links connect using soldered through-hole header pins instead of the original build's mezzanine connectors, but that is much simpler and lower cost. And the header pins do seem to be one component that can handle both electrical and mechanical function very well. And the trade-off, of course, is it's not easily detachable once assembled. And as my family will tell you, I get a lot of joy from informing people that Bendy won the Fine Art Award in the SAO contest. But Bendy's contest submission stated that it really should be considered for least manufacturable, so Hackety was warned. Bendy felt like less of an SAO and more like 8 PCBs in a trench coat. But the three winning, I wasn't going to turn it down. The three winning SAOs from the contest were distributed at Supercon Europe, and the designers received 100 assembled versions to keep. I mean, the value of that labor alone is insane. So Giovanni and Chris from Supply Frame, whom I believe could not possibly have been consulted in the judging process, got those three winning designs manufactured despite challenging conditions, not the least of which was dealing with my documentation. And there were some setbacks. Bendy showed up at Supercon Europe in pieces to be assembled there and missing one of his middle links. So he was somewhat vertically challenged, but still very handsome. I am super grateful to Martin Oehler, who came to Supercon Europe prepared to help others assemble and flash their Bendy SAOs there. So despite initial hiccups, Supply Frame clearly did nail the production process, because earlier this year I did receive my 100 beautifully assembled Bendys. And then, of course, what does one do with 100 SAOs? And this was the first thing. I also 3D printed some small stands, so they make nice desk toys now, and I actually still have some to give away. If you find me before they're gone, you can probably get one. So the aspect of this project that makes me the happiest are the remixes. Jen Will and Marcus designed a pulley system for a puppet Bendy, and maker Tom Keddy remixed the build for Pride Week, taking full advantage of its modularity. So Bendy boards pivot on an axis that's perpendicular to the PCB plane, and the next set of assemblies you'll see are designed to rotate on a parallel axis acting as hinges. And several times I've attempted to construct a modular hinged PCB system with the goal of making a wearable like a bracelet. There are existing official circuit board components that are hinged connectors, which I tried and found to be too bulky for a wearable, expensive, and with weak retention that's separated easily, so they're not really meant to bend repeatedly but stay in a flex position. Those were out for wearables. The next hinged or unhinged idea was also in my Remoticon talk, but it's one of my personal favorite hacks. I somehow got the idea of using dollhouse hinges for components. They're small, they're cheap, they're made from brass, which conducts and can be soldered, and I designed a custom footprint for them with screw holes for reinforcement, and they work, sort of. They're attractive, low profile, and appeared mechanically sturdy. However, it seems that having large, uninsulated, signal-carrying metal pieces that rub together creates, yeah, you see the problem, creates glitches in the signal and the resulting LED patterns. And more importantly, under repeated flexing, the pin from one hinge could actually slip out and contact an adjacent hinge, causing shorts, which is less than ideal for a wearable close to the skin. So, abandoned that idea, but I do not give up easily. So, I tried again. And this time, rather than using a hinge as a component, I used an existing component as a hinge. Each connector in this assembly is a male-female single header pin pair, and all connectors along an adjacent PCB edges line up along a common axis. And the male pin needs to be round for good rotation. I did not have those for this particular assembled version, so I took a page from Bohite's freeform circuit sculpture book and bent my own pins out of thin brass rod. I like to think I bent it like Bohite. In this first prototype, I had forgotten that sides pivot towards a hinge, so I had to flip the header pins on this build to the other side, but fortunately, that's an easy swap. Yay, header pins. And header pins have proved to be a cheap, accessible mechanism that's relatively sturdy under rotational motion, depending on how well I've got them aligned. They're vulnerable to stress when you pull the boards away from each other, so I've got some ideas for reinforcing them that I hope to implement in future iterations. And finally, after this talk, I hope you're feeling a bit more motivated to play around with your circuit boards in different ways. Super simple circuit boards that are easy to design can come together in really interesting structures. And despite the millions of connectors available on DigiKey and Mauser, header pins are frequently a good choice. I have brought many of the smaller PCB assemblies with me today, and if you want to get a closer look and play with the mechanisms, please come ask. I really love sharing my builds, and Supercon has been a terrific place for me to find inspiration and new ideas in talks and discussions with the amazing people here. And before I yield the stage, speaking of the incredibly smart and talented people here, I want to briefly share a story of the supportive nature of this community as well. When I arrived at Supercon Friday of last year with my 40 home assembled Bendy SAOs, I was horrified to realize I had designed the SAO connector backwards. I panicked, then realized I could flip Bendy's bottom panel, then panicked again when I realized how much work it would be to desolder and resolder 6 through-hole pins on all 40 SAOs. And even though it was prime Friday morning hacking and socialization time, an awesome group sat with me to carry out Operation Bendy Disassembly over the next several hours so I could finish the SAOs and still enjoy the first day of Supercon. And of course, since history repeats itself, I got here yesterday morning planning to install bodge wires on my latest SAOs, because of course, and instantaneously almost, another wonderful crew assembled out of thin air to make short work of the process. So thank you very much to Seth, Kevin, JP, Claire, Aisha, Darcy, and Ben, and anybody else I may have missed. Thank you for turning an anxious experience into a warm memory. And wait, one more. Thanks to everybody here for making this a cool, supportive place to put things together in unconventional ways. Whether the attempt is successful or not, the result is never boring. Thank you.
So many ideas. Thank